to the last talk of CBC 2020. So my name is Julian Renner, and I'm presenting some work that I did together with Thomas Jakowitz and Hannes Bartz from German Aerospace Center, Sven Puchinger, who's now with the Technical University of Denmark, Pierre Lodreau from Rennes, and Antonia Wartazzi, who is also affiliated with GOM. And in my talk, I will present a randomized decoding algorithm of Gabidulin codes that is capable of correcting errors beyond the unique decoding radius. So why is this interesting for code-based cryptography? The reason is that I would claim that most of the systems are based on a rather similar problem, namely on the hardness of decoding an error of rather small Hamming or rather small rank weight in a random code. However, in my opinion, there are also other coding problems that could be suitable for cryptography. And another one that I think is interesting is the following one. So first of all, I stated a bit informally, namely I say we have a relatively large error in the rank weight, in the rank metric. So it has a rather large rank weight. And we want to decode this error now in a Gabidulin code. And this is now special or different to before. Before we had a random code, and now we have a Gabidulin code, and we also assume that the structure of this code is known. And it was shown that based on this problem, you can build crypto systems. Just to mention two, there is this Ramesses system or the Vogel-Lodreau system. And they showed that systems based on this problem have then the potential to achieve rather small key sizes, and also rather small ciphertext sizes with encryption, decryption, and key generation algorithms that are very efficient. And as I said, what we do, or what I would like to do in this talk, is that I would like to show you a new decoding algorithm that we have designed. Okay, since there were already some talks about rank metric, I will go over the definition of rank metric very quickly. But still, I would like to show it to you in order to get you familiar with the notation that we use. So first look at this extension map, which I define here by ext gamma. It maps a vector of length n over the extension field fqm to a matrix with m rows and columns over the base field fq. So x is mapped to capital X. And the connection between both is that we fix a basis gamma 1 up to gamma m of fqm over fq. And if we perform the inner product of this basis with the jth column of x, we get the jth entry in the vector x. And then with this definition, we can define the rank norm of the vector x as the rank of its matrix representation, and the rank distance between two vectors x and y as the rank weight of x minus y. Now, what is important to note in the rank metric is the following property. This will become important for later, namely if we say we have a vector x with a rank weight w, then we can decompose its matrix representation x into a matrix A with m rows and w columns over the base field fq, and the matrix B with w rows and columns over the base field fq as well, and both are then full rank. Now, a very famous code class in the rank metric are Gabidulin codes. They can be defined by their generator matrix. So a Gabidulin code of dimension k and length n has, as I said, this generator matrix where we have in the first row this vector g here, and then we make q powers in the columns. And if the entries of this vector g are linearly independent over fq, then these Gabidulin codes have the properties, or the property, that the minimum distance is equal to n minus k plus 1, which means they are MRD. And furthermore, we know efficient algorithms that can decode errors up to rank weight n minus k half efficiently and always. So there's no decoding failure if the rank weight of the error is below this quantity. Now, with these definitions, we can formally state the problem that I just mentioned very shortly in the introduction. Namely, the problem we are interested in is this search Gabidulin problem. The instances that we are given a Gabidulin code with generator vector G, an integer W, where W is larger than n minus k half, but smaller than n minus k. And furthermore, we are given a vector R, where R is a code word of a Gabidulin code plus an error, where the error has rank weight equal to W. So once again, W is larger than n minus k half. So this is important. And then the objective is that one should find such a code word C hat from this Gabidulin code that we are given. And this C hat should be in distance to the received vector R, or in the rank distance of at least, or at most W, sorry, at most. And to emphasize this, so I put here a hat because this C does not have to be exactly the same as this C, but any C, so any code word of this Gabidulin code that is in distance as most W would be fine. Okay, so many people tried to solve this problem already, but all of them tried, or I would say most of them tried to solve this in polynomial time. And actually there was no algorithm so far found that can solve this problem in polynomial time, and it's also partly proven that this cannot be possible in polynomial time. So what we will do in the following is that we will show you an algorithm that solves this problem in exponential time. Now, to understand the algorithm that we developed, it is first interesting or important to understand what error and erasure decoder of Gabidulin codes mean. So to understand it, we first look at what is an erasure and rank metric. So here comes the property of rank metric that I explained before, namely if we have a rank weight or an error of rank weight W, then we can decompose its matrix representation in A and B. And furthermore, assume that you're given a subspace B hat of FQN of length n. Then we denote the dimension of this given subspace B hat with delta, and the dimension of the subspace B hat and the intersection of the row space of this matrix B here as epsilon. And then there are efficient algorithms known that if you give them as input, such as subspace B hat, the received word R, and the Gabidulin code, then they are able to correct this error always if the following condition holds. Namely, if epsilon, so epsilon is again the dimension of this B hat in the row space of B, is larger than this quantity. So if the intersection of this subspace B hat and the row space of B is large enough, then these algorithms are able to solve this problem. But the issue is that by the problem statement, we don't have any information about the error, and therefore also not about this matrix B or the row space of this matrix B. So what the idea of our proposed algorithm is that we repeatedly guess the subspace B hat and feed it together with the vector R and the Gabidulin code in such a Gabidulin error erasure decoder that I described before. And we do this until the time where the intersection epsilon of this B hat and the row space B is larger than this quantity, because then the error erasure decoder outputs a vector and we can check if this is a valid solution to the problem. Now, as you probably already assume, the probability that this intersection is large enough is not very high, and this actually determines then the work factor of our algorithm. So the work factor of this randomized decoding algorithm is then given by this quantity. Here we have the term n squared, which comes from the complexity of running one time the error erasure decoder. And we divide this by the probability that the intersection of our guessed subspace has a large enough intersection with the row space of the matrix B. And then we have to multiply it by this calligraphic n. And this calligraphic n is basically the number of solutions to this problem. Because, as I said in the beginning, this code word C does not have to be exactly the code word regarding this vector R, but any code word which is in rank distance at most W from R. Then we can quantify all these values and give a lower bound on it, which is then this expression. So it's not really nice to read, so I will not read it out. Okay. But what we did is that we now compared this work vector for parameters in order to see how efficient it is. And in the first step, we just used some small parameters which are not suitable for cryptography, but we used them to verify basically our estimation. And we verified this by basically running some true simulations of our algorithm and compared it with our analytic expression of the work vector. And here we can see that the simulation result is actually very, very close to our estimation. So I would say that our estimation is very, very good or very close to the true value. Then we compared our algorithm for parameters that were proposed in crypto systems, namely in this Ramesses and also in the Vogelodro. And we compared our randomized decoding approach with a generic decoding algorithm based on combinatorics and an algebraic generic decoding algorithm. And here we can see that our algorithm has a much smaller complexity. And we also compared our algorithm to this W key. This is a rather naive approach where we basically run a key equation-based decoder on the problem. And this leads at a certain point to an underdetermined system of equations. And if we search through the solution space of this one, then we get these complexities. Now, to give some concluding talks, what we did further in our work is that we showed that the work vector of our algorithm is concave in delta. And to recall, delta is basically the dimension of the subspace that we estimated. This means that the smallest possible value of delta equal to 2 xi, or the largest one, delta is equal to n minus k, are optimal in the sense that they minimize the work vector. And we also investigated approaches where we don't estimate row spaces of the error, but also column spaces. So this is also possible with error erasure decoders, or a combination of both. And we could show that this does not improve the algorithm. So basically the approach that I showed you before is optimal. Or not optimal, but at least better as these two ideas. Now what are future works? So the first one is that there was a new generic algebraic decoding algorithm proposed at the beginning of this year. And we did not compare our algorithm with that one. So this should be done. And another approach is, or another future work could be that one basically tries to find new algorithms to solve specifically this problem search Gabidulin problem. Okay, that's from my side. Thank you very much for your attention.
Thank you.